Okay, so SpinEcho. So now the problem is, so how does SpinEcho actually work? And really, what the problem that we're dealing with here is the problem that you have to run many copies of the block equation. That's really the fundamental problem, because the block equation describes a particular magnetic field vector, just one magnetic field vector. So it says, if you have this magnetic field vector, then here's what's going to happen to it. It's going to precess, and it's going to have T2 decay, and it's going to have T1 regrowth. There's three parts of the block equation. And so, and then it will tell you how that, what does that vector do? Well, it starts off over here, it gets really short, then it slowly grows up again. But the problem for, which we saw from the the lecture on the FID, is that unfortunately you got to run like multiple block equations, because since the B0 field is slightly different for each magnetization vector, each little chunk of magnetization vector, it's going to be decaying at a slightly different rate, and it's going to be precessing at a slightly different rate. And so how do we think about this? Well, let's just do two. So in real life, there's thousands of block equations that are running simultaneously, because each vector is in a slightly different B field, and it's getting out of phase, and it's decaying at a slightly different rate with all the other vectors. So basically, you have to run thousands of block equations to sort of like describe all the different vectors in order to describe one echo. So what we want to do today is let's just do two different block equations to sort of see where the SpinEcho actually comes from. So we'll start off. So what is the thing we're gonna do? We're just gonna do a SpinEcho, and so the SpinEcho, we do a 90-degree RF, and then we wait for a certain delay. So here's that tau delay. And then we do a 180 degree RF. And then we wait for that tau delay again. And then we record echo. So here's echo. And what I'm going to diagram out, I'll diagram out the several different points along this. So, so what happens right before we do the 90? Well, we should just be longitudinal. And then what happens, right after we do the 90? We should just be pure transverse. And then we'll say, what happens right before we did the 180? What's the state of affairs? And then what's the state of affairs right after we did the 180? And then finally, what's the state of affairs when the echo happens? So there'll be five conceptually different parts of the SpinEcho. So the first part is the easiest. So the first part is we have the our x-axis here, y and z. So the first part is we have our magnetization. So here's our, so we've waited a long time, a couple seconds, and so we have our MZ0 here. No signal coming out, and then we do an RF pulse, 90-degree RF pulse. So basically we just turn that guy into pure transverse. Now we're assuming that we're in the rotating coordinate system. So rotating coordinate system. And everything I'm going to draw is in the rotating coordinate system. So this guy just stays there. It just goes right down to the y-axis, and then it doesn't. It's actually in real life going around 123 million times a second, but we're just assuming that we're also going around 123 million times a second, so it's just stopped. So that's our 90-degree flip. So this part, this part is, t equals 0 minus. That means like right before the flip. And this now we're at t equals 0 plus, right after the flip. So use the same notation we were using in the other, in the original block equation. Okay, so now what happens? So basically that's this. We did, this was, A, B. So here's A, and here's B. Okay, so now let's do C. So now what happens? So now we have to deal with the fact that we've got slightly different B0 fields. And what is that going to do? In the rotating coordinate system, if the B0 field is slightly different than our rotating coordinate system speed, angular velocity, then these vectors will start to move. So they'll start to move in the xy dimension. So let's just draw, why don't I draw one more time point here. So this will be a better plan. What if we draw sort of like here and then wait until they get completely defaced? Okay, so here's, this will be better. So C, D, E, F. So we have, so we got rid of A and B. So A and B, we didn't have any T2 decay because the flip was so short, and so we could just ignore the T2 decay. So we just got a 90-degree flip. Everybody's still lined up exactly on the y-axis because there hasn't been any time for them to get out of phase. So now let's make a drawing just a little while afterwards. So we've still got some transverse magnetization. So let's make that. So here's just right before the flip, right after the flip, and now we're going to somewhere be in the range of sort of soon after the flip, so we can still see the vectors. They're not all completely jumbled up. So this guy is here, here, here. Okay, so here's the xy plane. XY plane. So now we have two vectors, and so let's just draw them. I'll draw one here, and then another one here, maybe coming out at you a little bit. Okay, so where do those project down onto the, make that guy a little shorter. So this guy projects down there, and this guy projects down here. So what does this mean? So what this means is, that one of these guys, so this guy is frequency lower. It's actually higher than B0. So why don't we just say, let's write it out. So the frequency, equals the omega 0, the center frequency plus small. So it's a little bit above the center frequency, which is why it moved in our rotating coordinate system. It moved relative to its original location, which was exactly on the y-axis. But this guy, the frequency of this one equals, omega 0 plus, bigger. So that guy is in the presence of a slightly bigger B0 field, and so it got say like an eighth of a cycle ahead. This guy got like a 16th of a cycle ahead. Okay, so that's kind of toward the beginning, and because they're spreading out, they're starting to spread out. They're actually going to start to cancel each other out, because remember, the signal is just the sum of all these vectors. It's just the sum of all these vectors in all these different directions. So what's going to happen? What's going to happen after sort of kind of a longer time, like right at the point right before we do the 180. So what's going to happen? What's going to happen there? Let's draw another one here. They're going to just completely spread around the circle. So if I draw, I just drew 2 there, but remember there's thousands of block equations running at the same time. So what's going to happen? So what's going to happen if we wait a longer time? What's going to happen is, here's our plane. We're just going to get a whole. We're going to get a whole kind of a whole little dish of vectors. Now, there's several things going on here. So there's been some T1 regrowth occurring, because that's why they lifted off the plane. Because see, this guy's down here. It hasn't had any time for T1 regrowth. These guys have started to regrow. The amount that they regrew was too big, because T1 takes a long time relative to T2. So I exaggerated how much they got toward the z-axis again, but they went up. But if you imagine what's going to happen after a while, they're just going to all spread out into this little dish. They'll all be at different places along this little dish that's lifted off the plane. And then what happens? They cancel each other out. Now they might not exactly cancel each other out, but they're certainly, because they're all spreading out to different amounts, there's definitely going to be a lot of canceling going on. And so that's the state that we're talking about, where we have long vectors, because T2 decay due to jostling with other protons hasn't occurred yet, but a static offset in the B0 field that's different for each of these guys. So each of these guys are in a slightly different B0 field, is going to cause them to get out of phase with each other. So the alternative is that there's no T2 magnetization left. But here's a case where there's a lot of T2 magnetization left, but you can't see it because it's all canceling itself out. So that's kind of the state of affairs at D. So this is the state of affairs at C. We're starting to sort of get canceled out, and here's the situation at D. So now what? So now we have our flip. So 2 ways of looking at the flip. We could just actually flip this whole disk over, which is actually what happens. But for the sake of argument, let's just imagine we did the 180 like around C instead of D, so that we can just look at what happens if we just flip 2. That's a legal spin echo. We could have just waited a smaller amount of time and done the 180 over here. That would make a spin echo. So say we just did the 180 before we had this complete spread into a disk, when we just had 2 that were sort of one's just a little bit ahead. So this guy's ahead. This guy's less ahead. So what if we did it in this state? So let's sort of think about what's going on. So in this case, what did we do? We flipped around the x-axis, okay? In this case, what we're going to do is we're going to flip around the y-axis. Now, you would get a spin echo if you flipped around the x-axis. That would be okay too. But it's often done on a different axis for having an effect so that we don't add 180 degrees to it. So that's actually, so if we flip first around the x-axis and then flip the whole mess around the y-axis, that makes our life a little easier. So we're going to talk about what this flip around the y-axis looks like. And so what happens when you flip around the y-axis? Well, you basically just take these guys and just rotate them around this, just rotate them around this axis here by 180 degrees. So it's basically just sort of flip this whole picture upside down. And so what does that look like? This is harder to draw, so I'll try to do a neat job of drawing this out. Okay, so here's that. Here's the plane. There's the plane. So now they're both under the plane. So both vectors are under the plane. So let's draw them. Draw this guy dashed because he's being interrupted by the texture on the plane. Now he's no longer dashed. So there's one guy. That's this one. So this is we'll call that guy frequency low. This is frequency high. So if we rotate that guy around, where is he going to go to? He's going to make it go out a little bit more. He's going to project up to a point here. So here's that. Here's the transverse magnetization from that guy. And the other guy, who is further ahead, is now going to be placed further behind. So I'm interrupting his little arrowhead there. Okay, so this guy will project up to this point right there. So here's that. The transverse part of that guy. So now you can see that what's happened is, so this guy, the shorter guy here, shorter because it's foreshortened, when you flip this whole thing around 180 degrees, now ends up behind. So this guy was the frequency high guy. So that one that was previously ahead, here's the frequency low guy. So basically the bottom line is, was ahead, now behind. And this guy, was behind, now ahead. So basically that's SpinEcho. If you can understand that with just the two of them, then basically you could understand with the whole disk. So imagine you have like a whole disk. They all got completely spread out. It's not that they just got spread out around the disk. Maybe they got like 20 ahead. So these guys could have, some of the fast ones, if there's a big magnetic field there, big B0 field there, they might have gotten 20 cycles ahead. But it doesn't matter. If you just take that disk and like flip it over, then what happens is the guy that's 20 ahead is now 20 behind. And so he'll be still going faster, and so he'll catch up slowly in exactly the same amount of time it took him to sort of get ahead. He's behind now, and he'll basically catch up and then come back into phase. So what is the bottom line, which is the echo. So what happens at the echo? So this was our position sort of E after the, this is E. And so finally, what happens during the echo? Well, during the echo, everything will be fixed. So here's the situation at the echo. So what happens at the echo is everybody just piles back in on top of each other. And you just end up with a vector that's right on the y-axis again. So we basically end up back to where we were here, except there's one difference. We're a little shorter. So we're a little shorter. So we're not as long as we used to be. So this is the x-axis, z, y, I, x, z, x. So we end up back exactly on the x-axis, on the y-axis, but we will have lost some amplitude because this is T2 decay. But it's important to see they're both on top of each other now. So there's basically, there's two of them right next to each other. They're both on top of each other. So everything will have been fixed. So they were, so think about the symmetry of the situation. So these guys were starting to recover, and so they had some positive z-axis. And so when we flipped them underneath, we made their z negative. So the z of this guy, this is the z-axis. So if you project, if you project this guy over here, you can see this guy has a z component, a negative z component now, whereas he used to have a positive z component. So we flipped the z around, and so when in the fullness of time, when you've waited exactly the same amount of time after the 180 as between the 90 and the 180, then the z recovery is going to sort of like get this guy back up to the horizontal. And then, the guy that was more ahead is now more behind, and so eventually he'll come back and they'll all come back into phase. And so this is the echo. This is the echo. Because the vector is nice and big, the sum vector is nice and big. Because, so what does that correspond to if we actually kind of look at the, look at our diagram of the way we normally look at, so like 180, here's the 180, so here's 90, here's 180, then here's that amount of time, and same amount of time later. What happens? So we get our initial big FID. So here's our big FID. And then when we do a 180, nothing, because if we did a perfect 180, we shouldn't have added any transverse magnetization. But this situation, when we're doing this 180, there's a whole bunch of magnetization. So this situation corresponds to this. So there's a whole bunch of magnetization there, but it's all canceled out because it's all dephased. And then we do our 180. We don't see anything from that because we didn't add any transverse magnetization, which is the only thing we can record. And then at this later point in time, everything comes back together and we get an echo. And basically, this part of the echo corresponds to this situation here, where everybody is all back in line. And this curve here corresponds to e to the minus t over t2. And this curve corresponds to e to the minus t over t2 star. So the bottom line is that we have all this hidden magnetization, which is not T2 decayed. So it's not yet decayed by the jostling of all these different protons, and the only reason that we can't see it is because local differences in the magnetic field caused everybody to precess at a slightly different rate, and so it spread all the magnetization out around the XY plane. And then since the signal equation, phase sensitive detection, signal is just the vector sum of all these local magnetization vectors, they cancel each other out. But there's actually a real signal there, and we can reveal it if we do another RF pulse, which flips them around, makes everybody head behind, and then we get a big signal. Okay, so that's the basic plan. So what we want to do in the second half is basically just go over the equations the simple equations that we use for calculating this amplitude. So like this isn't a good line here. Let's make that line up. There we go. Okay, so what equations do we use for trying to calculate this amplitude when we're considering things like, different flip angles, because we have to sort of make it general enough to before I go on, is there any burning questions about this or the drawings? I think I did the drawings look approximately better than I did them last year. So any questions at this point? We can also take some questions at the end.
So just for the last drawing, like the T2 decay part,
yeah.
Is that like they come back into phase when like they reach to the y-axis?
Yeah. So everything happens at the same time. So they come back into phase. They come back into the phase around the xy axis at the same time as they actually get right back to the y-axis. So all those things happen at the same time, and then you get this nice big coherent signal, because everybody, for just an instant in time, are all in perfect phase. And then, of course, they still are sitting in their slightly different magnetic fields, and so then you'll just decay. They will just decay away again, just e to the minus t over t2 star, because you still have all those local magnetic field differences. They haven't changed, and so they'll just mess things up again.
Okay, that makes sense. Thank you.
Okay, so that's spin echo. So that's the basic idea of spin echo, which is you just do a second RF pulse. So whenever you just you do one RF pulse, you just get T2 star. But if you do a second RF pulse, you can get an echo that actually reflects T2. So the strength of this echo, so this, the strength of this echo is described by e to the minus t over t2. So whatever, so what does that mean? It means like whatever the t2 value of the tissue at that point is, and whatever the time of the echo was. So what is the time of the echo? It's 2 times tau. It's 2 times that tau. And so, and then you just plug that into as the exponent of, of exp in MATLAB, and then that tells you what the amplitude of the echo is. But what we want to do now is a little more general, like what if we had a 30-degree flip? Then e to the minus t over t2 is not the right equation. So we have to consider like what. So it turns out to write out all the equations, I wrote them out in the notes, but to deal with 2 arbitrary flip angles, you end up with a giant page of sines and cosines. It's very easy to get all mixed up. And so what I just want to do is, rather than writing all that out, it's tedious and I can never remember it, well, we just want to write down what we would call like the 2 main operators. So basically these are rules for transforming an M vector, because that's what we're talking about, is we're talking about what do the block equations do. They just tell you, when you solve them, they tell you how to start with some M vector and turn it into another M vector after a certain amount of time. So the first main one is the operator is the effect of some arbitrary pulse. We'll say it's around the y-axis, because we can do it around the x-axis too. I'll just give a y-axis example. Okay, so some RF pulse. So this guy is RF pulse of some angle, RF of angle alpha. So it doesn't have to be 90. It could be like 35 or 75 or 112, doesn't matter. And so what is the effect on the magnetization? And so here's the components of the magnetization, and there's a prime there that, mathematicians use these things. It's just an apostrophe or what does it mean? Does it mean transpose the matrix, or maybe it means take a derivative? No, in this case it means rotating coordinate system. So we're not dealing with the sort of the precession mess. We're just dealing with these very slowly moving vectors in the rotating coordinate system. So that's what the prime means there, because they often use that in MRI to mean that. Or actually, why don't we put it? Should we put it down there? We'll put it over here, x prime. And that doesn't look so much like a transpose or a derivative. Okay, it's a little superscript on the subscript. Okay, so that's the x coordinate of the vector in the rotating coordinate system. And so how do we transform that? If we're doing some arbitrary flip angle, we need to use our rotation matrix, and if we write that out, it's whatever this mx was times the cosine of the flip angle minus the z component times the sine of the angle. Well, we'll show where that came from. And then for the my prime, nothing happens to it. So, let's just sort of see what we're doing. So what we're doing is we're flipping something around here's the z-axis and the y-axis and the x-axis. And so what we're doing is we're flipping something around the y-axis. So it's going around that way. So flip any old thing around the y-axis. And so if we flip it around the y-axis, then we don't mess with the y. Wherever it was, say it was, if it was pointing up here and we flipped it around the y, the y projection onto the y wouldn't change. So the y doesn't change. And then for the z component does. So here's the z prime component. And so that will be the x component times the sine of the angle minus the z component times the cosine. So this is like a rule for transforming your coordinates. It's a rule for essentially rotating the vector around some arbitrary vector. So here's just as an arbitrary vector. It could be any old vector pointing in any which way. And this is how you rotate it around. That's the simplest, the most compact way of writing how to rotate it around the y-axis, any old vector. So what is that? What is that? How did I write it out before? We wrote it out before as we have this rotation matrix around the y-axis, a particular angle, and what that equals is, this 3 by 3 matrix of cosine alpha 0 minus sine alpha, then 0, 1, 0, then sine alpha 0 cosine alpha. So that's the matrix, and then we're gonna multiply that, pre-multiply that matrix times so here's this guy's a matrix to rotate alpha around the y-axis, and then we're multiplying that by our m vector. And so here's the m vector. So that's just the components of the m vector. So m x prime, m y prime, m z prime. So that's just another way of writing out what we wrote here. So let's just work through one. So let's take the x one. So if we're trying to figure out the x output of this vector, we have to take cosine times mx, that's this guy, and then 0 times my, that's nothing in there, and then minus sine times mz, that's minus sine times mz. So this was just write out how to rotate around the y-axis. So that would be an RF pulse, effect of an RF pulse. And so now we want to consider what is the effect of waiting a while, like a delay. So the second thing is that we need to, because these are the things we need to do to calculate echoes, calculate the strength of echoes. So effect of some arbitrary amount of time delay. How does that change the magnetization vector? So this means like how does it, those last diagram that I had, that vector sort of lifted off the xy plane and it got shorter and it rotated a little bit. So what is the effect of the delay? So the effect of a delay is another operator. It's just whatever you start off with. So here's our starting vector. So whatever you start off with, and then how do we transform that? So we have to take the mx as I thought. So we have to do a cosine and a sine in order to sort of rotate the guy around in the xy plane. So here's the my prime times the sine. And this guy is the delta frequency, right? So we're not in the laboratory coordinate system where that would be 123 megahertz. Instead, it's a very low frequency due to the B field offset. It might only sort of gain like a cycle every 100th of a second or something like that. It's smaller. So it's just the offset that we detected out of the phase-sensitive detection. Yes, you can't escape phase-sensitive detection. So phase-sensitive detection gave you that frequency offset, the difference between the center frequency and whatever the frequency of this particular magnetization vector is. So that's that thing. And then you take that frequency, which is, angle over time, multiply it by time, and you get angle, and then you take a cosine of that angle and multiply it by the length of the mx vector. Okay, so this is how you calculate where that vector is going to end up in the xy plane. You have to know what the frequency is, which means you have to know what the B0 field is, the B0 offset is. And then last but not least, so we're not going to use these equations. I'm just going to show you what the transformation rules are, and then we'll give you the answer. If you want. Oh, sorry, and I forgot we have to decay it, because remember, it's e to the minus t over t2. So this whole thing is being decayed. Regular t2 decay, not t2 star decay. And so this guy is going to be minus x prime times sine of delta omega time constant plus my cosine delta omega time constant, also decayed by t. Both the x and the y decay. And then the last one is the z1, and the z1 has the different equation, the different block equation. So minus tau over t1. So this was just our solution to the block equation plus, the mz e to minus t over t1. Okay, so this is how we mess with the vectors to account for a delay. So this was when we do RF pulses and then delays. So what's the bottom line? So the bottom line is, if we run through pages of cosines and sines, because this was just for one transformation, but our transformation is we've got 2 RF pulses and 2 delays. So that means you have to resubstitute these things into themselves 4 times, because you start off with a magnetization, you do a flip, you do say a 90-degree flip. You use these things to calculate your 90. This was just for y, but say you did it on the x, you would use the rotation matrix for x. That's a 90-degree flip. Then you say, okay, whatever we got, doesn't have to be 90, it could be 30. Say we do 30. So then whatever we got out of this, we stick that into this side over here and figure out how it's going to decay after a time delay. And then we take that result and we stick it back into here in order to calculate what happens when we do our next flip. Say we do a 120-degree flip. And then we take that output and we stick it back into here and allow it to decay for another tau time, and then we get our output. That's why you end up with like hundreds of sines and cosines. But the bottom line is, after we do all that, our final answer is relatively simple. So it's whatever the starting magnetization was times just the sine of the first RF pulse and then times the sine squared of the second RF pulse angle divided by 2 times e to the minus t, sorry, not minus t, minus 2 times tau over T2, yeah. So why is that 2 in there? We'll sort of get back to that. So this is the equation for, so this is the bottom line. So this is the one we'll put some stars on that. So what is this? This is the equation for the amplitude of SpinEcho with 2 arbitrary flips, alpha 1 and alpha 2. Okay, so that's the most general one. So that doesn't look like e to the minus t over t2, because that's what I always write down. I always write down, here's an RF pulse, and then so here's the RF pulse, and then here's the 180, so 90, 180, then we wait tau later, and we get an echo. And then we draw this line like here, and that one's e to the minus t over t2 star. Then we draw this line here. And that guy is e to the minus t over t2. And so how come that doesn't look like that? Well, let's just consider a special case. So if we consider a special case where the second flip angle is 180 and the first flip angle is 90, then 180 divided by 2 is just 90. And so in that case, that's just the sine of 90. So you could write it out as, a much a more simple equation of sine of 90. So what is the sine of 90? So let's just look at the sine of 90. So here's sine. There's 180 right there. There's 90. Happens to be 1. So if we take this equation, so the sine of, if the first flip is 90, the sine of 90 is 1, so we got rid of the sine. And then the second flip is 180, well, that's 180 divided by 2 is 90. The sine of 90 is 1, so all the signs disappear. So basically if we have, alpha 1 equals 90 and alpha 2 equals 180, simple. So what is it in that case? It's just mz, whatever the starting magnetization was, times e to the minus t over t2. Sorry, minus te over t2. So where did the 2 go? Well, what is the te? So the te is basically just this time. So this is the time of the echo equals 2 times tau. So everything goes away, and we just get mz times e to the minus te over t2. And there's, so that even gets more stars, 4 stars for that one. But this is the general equation that you would use to calculate how strong a spin echo would be if you don't happen to have like you don't happen to have 90 and 180. But there's another special case, one more special case. What if we have, you know, alpha 2 equals twice alpha 1? So what if we have, instead of 90 and 180, what if we have, say, 30 and 60? There's another special case where the second flip angle is twice as big as the first. If you do that one, then you get another simple case, which is mz0 sine cubed of alpha 1 times e to the minus echo time over t2. So that's another simple one. It doesn't get, so we'll give that one 2 stars, give that one 4 stars, this one gets 3 stars. They're all the same thing. So these were just special cases, but common special cases. And so if you want to see all the sines and cosines worked out, it's basically just taking these 2 rules and just repeatedly applying them. You know, do a flip, wait some time, modify it, stick it back in, do another flip, wait some more time, modify it, see what you get. Okay, so this is the amplitude of the spin echo with 2 arbitrary flips. Okay, so I think, David, we can turn off the recording just in time.